problems here than incentives.
You guys, can I have a show of hands? How many are going to be on Friday for the contest?
Oh, yes.
Wow.
Not here, Weaver Building, right?
Yes.
Is it the same room that it was last year? That
Yes.
big
Always
room
same
where they
room.
teach art?
Always same.
All right.
This is going to be a really large room for the math contest.
It generally is. Generally
Chris.
full.
I have a question. I was reading the flyers. It didn't say anything on there. We don't have to sign up and just show up.
Right.
Right or nay.
Actually, it is on the Scantron, and I think it is.
Do you have to bring a Scantron?
No, you don't bring anything unless you want to calculate. It could be graphing. I can't remember if it's on the Scantron, but on whatever the form is, yeah, it's not Scantron, but the form will say, who's your professor? And so that's how Professor Myers, when he grades them, he'll put the Balagai ones on Balagai's desk in my office. We're just not going to do that. So that's how he'll know who took what. I'm sorry, I have had no sleep. Did I send out an email this morning about the room change for the math club, the calculus club?
No.
Gosh darn, I'm so sorry. I'll get on it today when I get home after I pick up kids. I did get the room reserved. They allowed me to do it. So we'll be in Weaver 110.
Sounds good.
Oh, the big room?
Yeah.
For
I
the
remember
calculus club?
CC
Oh,
I remember
awesome.
CC, Mary Beth, Pattengale, and Dominique.
Yes. Or, well, Dominic's already on the list, so.
Hey,
Oh, is he okay? All right.
if I give you my tablet on Friday, can you record Calabresi's?
Oh, you're not going to be here?
Yeah, both Katie and I have a tutor meeting, and
Again? How many
Again.
times do you guys have meetings?
too much, and we all know the material,
What
so
do you
I don't
discuss?
how to factor.
Really?
Yeah.
And who teaches you?
Well, he just has us come up and show him on the board
Oh,
how
James
we would
Wasabi.
factor. Yeah,
Oh, I didn't know that.
but yeah, we have meetings like almost
I see
like
you
every
talk
couple
about
weeks now.
Issues.
Yeah. Oh yeah, and we complain about students.
Do you really? You would never want me to complain about you, would you?
Huh? Well, you could, just don't tell us about it.
So you guys, today, I want to get a lot done. I really want you guys to be good at solving PEs, and I want to look at it a couple different ways. I really can't get started unless you guys are familiar with some basic types of forcing functions for which you and I can have an easy chance at generating some particular trial solutions. So, I think if your forcing function looks something like this, I think the first thing I should do is solve the corresponding homogeneous case. But you guys, when I write down the homogeneous differential equation, actually I take that back. I'm not going to write it down. I'm merely going to write the corresponding characteristic equation. Is it just simply this thing right here? Is it this simple, I should say? And so at a moment's notice, I can write the complementary solution just like that. I mean, just like that. I mean, like that. Really?
To the 2x plus c2 e to the negative x.
Right? Sweet. Somebody there.
Can you put your rules back up on the board again?
My rules?
Yeah, for when to sum in the e's.
Oh,
You know what I'm talking about? Just for visual aid.
You're thinking of this.
Yeah.
Jason's okay. If my character's equation looks like this, and to solve in that characteristic equation, which by the way is solving a math B equation, if I end up getting two distinct real solutions, then the corresponding solutions to the homogeneous differential equation, which are going to, in the end, be my complementary solutions, are going to be nothing more than this. C1 e to the R1x plus C2 e to the R2x, where R1 and R2 are merely the two distinct real roots of that characteristic equation. And I proved that to you in class. I proved it. I also proved that if you have only one real solution, using that funky new technique I have for solving PEs called reduction of order, then it is the case that the complementary solution could be expressed in the form C1 plus C2 times x, all times e to the Rx, where R is your only one real solution to the characteristic equation. By the way, you better get used to this. Notice how these two solutions look like an e to the rx and an e to the rx. They're not. One's an e to the rx, one's an x times e to the rx. That introduction of the factor x literally removes the duplicity of that r guy. That's really important. That's something you're going to see recurring over and over again, even today in class. I also maintain that I proved to you in class that if I have solutions to that characteristic equation of two non-real complex solutions. You guys hold on a minute. I need to use my razor. I meant to say two distinct. We're going to fit that in.
Just put a little carrot
How about nowhere?
with it. Yeah,
Yes, these are real coefficients. I think those complex, non-real complex solutions are always going to come complex conjugate pairs. So I think it's for free. And I think my complementary solution is going to look like, how about an e to the alpha x times c1 cosine beta x plus c2 sine beta x. If you guys allow me just to say out loud in English, that the complex solutions are the form alpha plus or minus beta times I. So I think that's what my complex solution is going to look like, relative solutions to the characteristic equation. Yes?
Would you like us to commit these to heart?
No, you already have. I assume you already have. I really
Right,
do.
Of course,
Of course.
of course.
You guys, let me see if I got a decent pen. Michael?
Okay, so for 23, where it's talking about C2 sine dx, so when we're solving for like factors of like r, or roots of r, and we get like a plus or minus an I term, so the negative I term would represent the sine dx then?
Yeah, so if you got these two solutions right here, r being equal to 2 plus or minus root 3 times I think the 2 is nothing more than my alpha. And the root 3 without the I is going to be my beta. That's how I use them. And everybody, I maintain at this stage of the game that I need to look for my particular solution. And to look for my particular solution, I've got my two eyeballs not moving in motion the same way. I've got one eyeball on my forcing function, and I've got one other eye sitting on my complementary solution, and I want to make sure that I've got no duplication. Now, when I take a peek at my forcing function, it looks to me like it's a quadratic expression. So I'll probably come in and say, well, I think my trial particular solution should look like the most general quadratic equation or quadratic function I have, which would look like this. It's just my other eyeball's looking at the complementary solution, looking at the underlying components of the basis for that solution space, and make sure I don't have any duplication. Oh, look at that, these are exponential, those aren't. So I guess it's no duplication. You guys there?
Not yet. Well, I mean, we're not there yet.
Well, at least you're okay with my fact that I'm okay with that particular solution. Okay. Shoot, I lost track. What am I trying to do? I forgot. I said, what am I trying to do? I forgot.
Find A, B,
Trying to
C.
find A, B, and C. This is the method of determining coefficients for constant coefficient differential equations, particularly non-homogeneous case. And so, I think I need to pick this piece up off the board, slap it in for Y all over the place, and solve for A, B, and C. That means I need to differentiate once and twice. In this example, you guys fall asleep. It's that easy in this example. But when I pick these three beasts up off the inboard, slap it back at my differential equation, I think I get this. I think I get my 2a minus 2ax minus b minus 2ax squared minus 2bx minus 2c being set equal to my 2x squared minus 3. Now, if I locate or co-locate all the terms involving the variable x squared, oh shoot, there's only one of them. Co-locate all the terms involved in the variable x and factor the x out, I think I get a negative 2a minus 2b. And finally, combining my constant terms, or at least putting them together, would that give me a 2a minus b minus 2c? You guys, are we there? Oh, by the way, I can now equate coefficients, but equating coefficients gives you 3 equations, 3 unknowns. If you want to, you can use chapter 2 and 3. You can use Gauss-Jordan elimination on automatic matrix, inverse matrix method, or Cramer's rule. I have a right to say that fast. But I don't want to. I'm tired. Equating coefficients? Just equating coefficients of x squared, just like you guys did with the partial fraction decomposition technique for integrating. I think clearly my coefficient of x squared on the left-hand side has to be equal to that on the right-hand side. I think that implies a is equal to -1. I apologize. I made this example up out of thin air. I was hoping my numbers would be more interesting.
Oh, it's very interesting.
And I think equating coefficients of x is simply going to give me that -2a minus 2b is equal to 0. But doesn't that imply that b is equal to +1? I'm so unhappy. And finally, equating constants. I think that tells me that 2a minus b minus 2c is equal to my -3, but plugging in my values for a and b, I have no idea what that is. Is that a -3 minus 2c equals -3? Aw, jeepers. I really did not mean that to happen. And so I think my life's just a little easy. Oh, by the way, it's this easy. We could state a solution. I think all solutions to my DE can be expressed as C1e to the... Yeah, I don't remember, I'm sorry. Yeah, just put everything in. You said minus x squared plus x. So I've got my complementary solution, and I've got my particular solution. Oh, you guys, I just can't wait. This is so much fun. If this term weren't here, can you imagine what would happen with this solution? Is there anybody in this room who's taking circuits? Michael, that's it, just Michael.
Wasn't Vince isn't here, but Vince is taking it. Yeah.
In circuits, you learn how to separate the solutions to certain circuit issues. And when I take a peek at this piece right here, it's sort of like this function is just it's function. It's going to be there for various different values of x.
Are we going to get into any circuit theory in here?
And I'll even prove to you why the circuit equations look this way. But I might refer to that as a steady state solution, or it's just more of a transient solution. Because as x increases our bound, that's going to go to 0. Now, if I had a differential, you guys, can we just not finish these? A couple of them? Can I just talk about the technique? All right. Number 2. And you tell me if I'm annoying you by changing things so fast and not finishing. I'm just trying to save time on the clock. Do you guys agree that my complementary solution does not change? Do you agree my particular solution is going to change?
I don't think you're going to have one. Or rather, I think it can be expressed as a linear combination of the complementary solution.
Do you really think so? Because I think e to the 5x is not a multiple of e to the 2x or e to the -x. Or even a combination there, right?
You're right.
Okay, let's agree. Michael?
Yeah, because on that one, the forcing function is going to make the particular solution going to be an a times e to the 5x, and then
Done.
solve.
I think you're done. I think life is that easy. So I get a times e to the 5x. I'll differentiate once, differentiate twice, pick it up off the ink board, slap it into DE, solve for the coefficient a, and I'm happy. Okay, as long as you guys are right. Remember, you're paying money to be here. You tell me if I'm just skipping too much. I just want to raise the level of complexity. So I took care of what a Pauli solution looks like, a Pauli forcing function looks like. That's how I make my decision of y sub p is, use my method of undetermined coefficients. For an exponential example, I just did that as well. Here's another one. Now what will my trial particular solution look like? Anybody?
A times cosine 2x.
A times cosine 2x.
Period.
I think it should should be period, here's why. Because when I differentiate that, I get a sign. Oh shoot, but I gotta differentiate when I slap back into my DE. So when I look at that forcing function involving either a sine or a cosine or both, through the differentiation process, I'm still gonna generate both of them. I think I need both of those included in my trial particular solution. I think I need to add to this a b times the sine of 2x. Do you guys see my point? Chris? Okay. Only because I've got to pick the thing up off the board, plug it back to my DE, I'm going to generate sines and cosines.
So you're, hold on.
Yes,
You're
hold on.
always, for your particular solution, you're always looking for the most general, but the simplest, most general case.
Yes, I agree with that. And you know what, you guys, I think I'm done. I think when it comes to the standard types of forcing functions for which you and I can use this method of undetermined coefficients, it's going to involve a polynomial function, excuse me, exponential, or sine and or cosines. If the forcing function is something else, I'm afraid I'm going to have to show you different techniques.
I was gonna ask, what was that logarithm?
Yeah, there are other techniques. The other techniques involve something I'll refer to as variation of parameters, and a technique I'll refer to as using Laplace transforms.
Sounds gross.
And another, oh, they're beautiful, they're so nice. Just remember, when I teach this course, it's typically students' favorite part. Trust me. And then I can use power series solution technique. And that's the other end of the spectrum. That's usually students' most non-favorite part.
What?
I know.
The power series is fun.
Oh, briefly,
Yeah.
I asked. Yes, sir.
Yes, sir.
Just briefly, if you were to use power series expansion, that would just reduce it to a polynomial equation, right? Essentially.
I hate to use the word polynomial because when you use the word polynomial, it's going to have a degree. That means n is finite. Whereas a power series, you can think of, if I use these words, as an infinite polynomial. It doesn't make sense, so I just refer to them as power series because it's infinitely many terms. So I try to steer away from the word polynomial when I'm looking at a power series. So I'm slowly raising that level of complexity. What do you think?
X squared, a times x squared times e to the 5x.
Keep going. Keep going.
Plus c times x. No, b times x.
It
Plus
doesn't.
c.
Oh my God. In other words, you guys, I think this is more of a general form of a function that is the type that's in the forcing function's position, namely the product of an exponential function and a quadratic function. Then I have to go through the process. There's a bit more work there, isn't there? In this example. What about 5?
A times x squared plus, well, there should be beginning parentheses, plus b times x plus c times parentheses cosine x plus sine x.
Say it again.
Yeah,
I couldn't hear that.
times sine 3x. No?
Yeah, I disagree.
I don't know.
The blood's rushing out of my arm.
Cosine
I already rushed out
3x?
of my head.
Cosine.
3x.
That's it?
No.
No.
dx squared plus ex plus f times
kidding.
sine of 3x. I'm not kidding. There's a lot of work there. So now you got to solve for 6 different constants.
Why do they have to be different?
I have to have freedom. I have to have freedom because I need to accommodate for the most general type of forcing function because typically those constants are going to be different. You might get lucky, but typically they're going to be different.
Don't ever assign us one of those problems. Ever.
You're not going to like my next exam. What about this? Anybody?
AX squared.
AX.
Squared.
I get 3.
Cubed. How come it's cubed? Squared. plus CX plus D.
I can't hear you.
What?
Plus D?
No.
Times E, parentheses.
Good, close, times e to the negative x. Yeah.
I don't get it.
Here's why.
Oh, that was gonna be the question, why is it actually?
That's what it should be. My two eyeballs are moving in different directions. I got one eyeball on my forcing function, that's the most general form. My other eyeballs on my complementary solution, should use duplication, I'll introduce a factor of x and distribute it. Did you see it?
Yeah.
Now, if you made the mistake of putting in a distribute this exit, if you made the mistake of putting plus d, it's fine. You made the mistake. You'll find a constant for d. It's just that in your particular solution, there will be that one term that says 7 times e to the negative x. Now when you write your final solution, you just absorb it as this constant coefficient here, call it c sub 3, where c sub 3 is c sub 2 plus 7. Do you see my point? It's not going to hurt you, I just wouldn't do the extra work.
So the general algorithm for doing these is first figure out what the simplest general
Yeah.
case is for the particular solution.
Yes,
And
yes,
then
yes.
you check to see if you have duplicity within your
Perfectly put.
complementary.
And you want to remove the duplicity by introducing more and more factors of x, however many times you have
Is
duplicity.
that the only way to get rid of duplicity, or can you introduce other factors?
It's the only way I'm going to remove this duplicity, but it's not the only way I can solve this deeply. You guys want to help me with this? Let's just play for a minute. I want to generate some whole new theory. Help me with this. Just help me. A
Times D.
E
AX.
AX minus A E of AX equals. Oh, you know what? This differential operator acted on e to the x in such a way it sent it to 0. Can I use a new word? I will say this differential operator annihilated that particular function. I'm going to introduce annihilators next.
What does it have against the function?
It just likes to absorb it. It's not a negative thing. It's a beautiful thing.
Okay.
You'll see in about 5 minutes, you guys. I'm going to use these annihilators to cheat. They're beautiful little mathematical hammers that ding on non-homogeneous DEs to instantly transform into homogeneous ones. Oh yeah, you'll see it. Do you think this differential operator will annihilate x times e to the x? Yeah, I don't think so either. Can I just show you why? To differentiate this product, I get the first times the the second, plus the second times the first, minus a times x times e to the x. Now I gotta confess, this ends up being nothing more than just simply e to the x. But it didn't annihilate, did it? Chris?
But we can throw in another annihilator again.
That's beautiful. And so if I apply the differential operator twice, I think I differentially operate on this, which means I'll differentially operate on this, but I've already proven to you that that's the annihilator for this. So I might say this in English. Extra factor of x in there, piece of cake. I think this differential operator raised to the second power will annihilate it. Can I extend that?
Can you legally do that, though? I mean,
I
just
just
raise it
did.
to the second... Well, I know you just did, but I mean, can you explain how you were just able to raise it to the second power?
Well, raising the second power simply means I'm doing it twice.
Okay.
So when I had that d minus a squared of this stuff, I know I didn't write it, Brad, but I was simply saying this. I'll differentially operate on the differential operator acting on x e to the x. Now, everything you see above the brace is what you see inside the set of parentheses. And then I differentially operate on that.
Okay.
And since these are polynomial differential operators, they even commute, which is what you and I discussed.
So can we differentially operate as many times as we want? Is that basically what we're getting out of
Oh,
this?
thank you so much. So you're saying differentially operate k plus 1 times?
Yeah.
Will eventually annihilate that business.
Okay.
Yes, Chris?
K plus one, I don't know, can you prove that? It was easy to show that for a degree or two, but.
Yeah.
Okay, I'll prove if you like. I have to think about it. How do you want me to prove it?
Well, I don't know.
Sure you do. How do you want me to prove it? If this is true for any positive integer k, how would I prove it?
Induction.
Thank you. So by mathematical induction, do you mind if I don't show the first step? The first step of mathematical induction is a piece of k. Allow k to be 0. I've already proven to you that d minus a annihilates e to the ax. I've already proven that. Can I change my notation if I do this, you guys? Can I change the k's to n's? Because I like using k's within the proof of mathematical induction. Do you mind? It's just a variable name. But to inductively prove that this is the case, let's you and I assume that replacing n with an arbitrary value of n like k. Let's assume that if I differentiate operate k plus 1 times on x to the k times e to the x, let's just assume it equals 0. Let's assume it's an annihilator. We will show that I'm replacing k with a k plus 1, that this particular function will be annihilated as well. That's what I'm trying to prove. Let's give it a shot. To show this is true, look, it's an equation I'm trying to establish. I'll just start with the left-hand side and see if I can mathematically do this. I get the right-hand side, which is just 0. So differentially operating k plus 2 times on stuff. Isn't this the same thing as differentially operating once on differential operating k plus 1 times on x to the k plus 1 times e to the x? But that's the same thing as differential operating on k plus 1 times anyways, a product. You guys attack me if you don't like what I'm writing. That being the case, I think I'm left with d acting on, well, let's just do it. If I differentially operate on x times this thing, I'll use product rule. Product rule says I get the derivative of the first times the second as is, plus the first as is times differentiation on the second. But that's just simply going to be d acting on, okay, I got to slow down, you guys. If I differentially operate on this once, what do I get? 1. Twice I'll get 0. Well, I've already shown the first case, so now it's going to be the second. And 0 times anything is just 0. Plus, shoot, where am I at? I lost it. So annihilating this is going to give me,
0.
this is 0, where'd you get that?
From the assumption.
From my inductive hypothesis, that's what I assumed. So using my inductive hypothesis, I think it's going to be 0. 0 times x is just 0. But differentially operating on that, what do I get?
0.
Oh, piece of cake.
Does that work for negative integers as well?
Well, no, I can't discuss negative integers because it has no meaning to differentiate a negative number of times. I mean, I suppose you could think of anti-differentiation, but it's going to run into problems with constants. Oh, you guys, I can be stronger than this. I think then that differentially operating with this operator n plus 1 times is going to annihilate anything in the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a sub 2x squared plus a sub 1x plus a sub naught all times my e to the x.
Because it distributes.
It does. And I think differentially operating too many times on something that's lower powered is still going to bring it to 0. It's just going to bring it down to 0 faster. And I also maintain, can I give myself some room? I also maintain, I don't want to erase it if you're still writing.
Yeah.
You got it?
Yeah, I read it already.
I maintain that if A is equal to 0, oh shoot, that's a piece of cake. It just means that differential operating k plus 1 times is going to annihilate. It's going to annihilate this Paulin expression. You guys, that's free, isn't it? All I really did was I replaced A with 0. That's easy. The only thing you need to worry about is when it comes to sines and cosines. So you guys relax for a minute. Let me do all the work. It's going to take me a few minutes. You check out what happens when it comes to this differential operator. Acting on this. Because I maintain that this is going to give me, you guys tell me if I'm skipping too many steps. The d squared acting on this is really just going to be a d acting on its derivative. Can I differentiate? That'd be the first. Times through the second. Plus the second. Times through the first. And I think I've got a minus 2 times a times, oh, you know what? I got to differentiate again. I'll just cheat, I'll copy what I have. Is that a negative b e to the ax sine bx plus a e to the ax cosine bx? Oh shoot, I missed a few things, sorry. I got my a squared plus b squared times the stuff. Does that give me a squared e to the ax cosine bx plus b squared times e to the ax times cosine bx? Now, maybe differentiate again. Shoot, you guys, there is a bit of work here. Darn it. Probably wrong. So, the first times through the second. Plus the second times through the first. But now I got to differentiate, shoot, look at that, that's that product. And to differentiate that product, I get the first times through the second. Plus the second times through the first. Oh shoot, I forgot these other terms. Let me distribute. Is that a positive 2ab e to the ax sine bx? Is that a minus 2a squared e to the ax cosine bx? And I've got these last two lingering terms in here. Is that an a squared e to stuff cosine bx plus b squared times all this stuff? You guys, I'm sorry for all the writing. That's why I told you to relax for 5 minutes. And let me come with my color pens. Let's see if I can clean up. Here's a negative b squared stuff with cosine. Oh, here's a positive one. Tad bit of cancellation. And how about when it comes to this minus ab e to stuff? There's two of them. Well, I should say negative 2 of them. Oh, but you know what? Look here.
There's another AB to the stuff.
They're gone. And next, with my black pen, what have I not combined? How about an a squared stuff? Oh, here's another one. That gives you 2 of them. Oh, but there's minus 2 of them. They're gone. I've just proven to you that this differential operator, polynomial differential operator, annihilates that particular product.
So, I had to step out for a second, but that differential operator you got up there, did you just
I made it up.
made it up?
And now I proclaim that if ever you want to annihilate something like e to the ax times the cosine of bx, there's your annihilator.
And so that's the one we're always going to use in that situation?
That's exactly what I'm going to say.
Okay.
Chris?
Who the heck came up with that?
It's actually really easy. If you just go back to the characteristic equation and you use a quadratic formula. You come up with the same thing in terms of the coefficients. You really do. But at least you guys got to relax and see me prove that it really does work, so now you believe it. You just now have to know it. And I maintain this is also going to annihilate this. Proof's the same. Do you mind if I don't? But that means it's going to annihilate this. But that means it's going to annihilate this.
It's annihilating everything here.
Oh, not quite.
It's on a rampage.
If I had an extra factor of x, oh, it's not going to happen. I'm going to do it twice. Or maybe I had this to the x, or the k power. That'll be k plus 1. Or maybe it's a general k order polynomial function. Same thing.
So is the reason why we're doing this is to get rid of, or to compensate for like duplicities?
Not quite. It's just so I can to get a special mathematical hammer to ding on a homogeneous DE, transform it into a non-homogeneous one. Since you asked, can I finally put this to practice? I spent 15 minutes talking theory. Let me come back and solve the DE, the one over there, by not looking necessarily at the homogeneous case. If I were to dive in, excuse me, and rewrite the left-hand side using differential operators, wouldn't that look like a d minus 2 times d plus 1? Acting on y being equal to x squared e to the negative x. Do you guys agree? Be honest. And I think there's a bit of work here to do, so I claim defeat. I'm going to magically transform this into a homogeneous differential equation by doing the following. Taking my x squared times e to the negative x, and I'm going to annihilate it. And to annihilate it, I think it's going to require a d
Minus.
I can't hear you.
So d to the k
Plus
3.
1.
Plus 1. The third. Security. Oh, I can't do that to the right-hand side without doing it to the left-hand side.
Briefly.
Yes, oh wait.
Didn't we have e to the positive x before? No, it was e to the ax, right? And our a is, okay.
Or a is negative 1 in this case. And I maintain that what I have on the right-hand side of the equal sign is just 0. Oh, come on, nobody jumped. I just annihilated the forcing function, and now I want you guys to kick back, put your feet up, and subclassify this DE. This is a DE that is
Incorrect.
incorrect. Oh, really think so?
You didn't put your d plus 1 to the third.
Oh, yeah, I did. I just multiplied by d plus 1 to the first. I got d plus 1 to the
Oh, I
fourth.
didn't see the 4 there.
My apologies. That being the case, I just transformed my
So it's a linear homogeneous differential equation.
Yes, it is. Ah, but it's homogeneous. That means I get to write my solutions down for free. Write my solutions down. I think I've got y as a function in x being equal to, let's see where I'm at. Is that a c1 e to the 2x
Yes.
plus
C2.
c2 e to the
Negative 1.
negative x plus plus.
That should be it.
I heard that. Somebody said plus a. I don't want to use my C sub i's anymore because that corresponds to a complementary solution. Now that I got my complementary solutions listed because I can just glance at the original DE, I know what they are, I think I should write plus a times x e to the negative x plus b times x squared times e to the negative x plus c times x cubed e to the negative x. Do you guys agree? And you know what? This really doesn't save any time. It really doesn't. I just think it's elegant. It doesn't save any time because I got a lot of work to do. Now I've got to use my method of undetermined coefficients to find values for A, B, and C. Shoot, I've got some work to do. That means my trial particular solution is gonna look like the ax plus bx squared plus cx cubed times e to the negative x. And we're gonna have to differentiate once and differentiate twice.